Now I'm going to be discussing International Classification of Diseases (ICD) system. So ICD-10 fundamentals and medical context. So the International Classification of Diseases 10th revision, that is ICD-10, represents a sophisticated medical coding system developed by the World Health Organization (WHO) to systematically catalog health conditions. This alphanumeric coding framework serves as the global standard for medical diagnosis, reporting, and healthcare data management. Right now, ICD-10 structure and organization. So first, we have the character format. We have 7 character alphanumeric codes with specific positional meaning, where the first character is always alphabetic, indicating the chapter classification. Then second, third characters are numeric, representing the category of disease or the condition. And then we have the fourth to seventh characters, which are which add additional specificity through subcategories and extensions. So now chapter-based classification systems. So the ICD-10 divides medical conditions into 21 distinct chapters, each covering specific body systems or disease categories. So we have chapter 1 till chapter 10. So chapter 1 has this code A00B99, which are infectious and parasitic diseases. Then chapter 2 C002D48, neoplasms and tumors. And similarly, you can see blood and immune system disorders, endocrine and metabolic diseases, mental and behavioral disorders, nervous system disease, eye ear conditions, circulatory system diseases, respiratory system diseases. So these are basically classified on the basis of the chapter. And we have respiratory system classification deep dive. So let us go over chapter 10, which is J00 to J99. This is the respiratory chapter, which demonstrates ICD-10's hierarchical precision through detailed subcategorization. Right, the respiratory infections J00 to J06. We have acute nasopharyngitis, sinusitis, pharyngitis, acute tonsillitis, and laryngitis. Acute upper respiratory infections of multiple sites. Then influenza and pneumonia J10 to J18. Seasonal influenza with respiratory manifestations, viral and bacterial pneumonia, pneumonia due to specified organisms. Then chronic lower respiratory diseases J40 to J47, COPD, that is chronic obstructive pulmonary disease, asthma with various triggers and severity levels, bronchiectasis, and other chronic conditions. So this systematic approach enables precise medical documentation, ensure billing accuracy, and epidemiological research. Now, fundamental concepts in word representation. So the challenge of computational language understanding. Natural language processing, which is NLP, which faces a fundamental challenge, that is computers operate on numerical data while human language exists as symbolic text, right? So converting words into meaningful numerical representations requires sophisticated approaches that preserve semantic relationships and contextual information. Basic vectorization paradigms. So abstract representation learning. Modern NLP employs deep learning approaches that map input text through feature spaces to create abstract representations. This transformation process involves 3 key stages. That is, firstly, input space, which is raw textual data requiring numerical conversion. Then feature space, intermediate representations capturing the linguistic patterns. And then the output space, task-specific numerical vectors for machine learning. We have four primary representation categories. First is basic vectorization using one-hot encoding, bag of words approaches. Then distributed representations using dense vector embeddings. Then universal language representation, context-aware embeddings, BERT, GPT, and handcrafted features, linguistic rule-based representations. Now the distributed hypothesis, theoretical foundation. So the core principle of the distributional hypothesis. So it was articulated by J.R. Wirth, and it states that you shall know a word by the company it keeps. This principle suggests that the words appearing in similar contexts tend to have similar meanings, right? So theoretical underpinnings. Zelig-Harris formalized this concept, proposing that linguistic items with similar distributions have similar meanings. This hypothesis forms the theoretical foundation for modern word embeddings and statistical semantics. Practical implications. Words like cat and dog appear in similar contexts, pet-related discussions. Then technical terms cluster in domain-specific contexts. Synonyms exhibit similar distributional patterns across large corpora. Now, traditional text representation approaches we'll discuss one by one. So firstly, we have one-hot encoding. That is binary vector representation. Mechanisms and implementation. So one-hot encoding maps each unique word to a distinct position in a binary vector. For a vocabulary of size v, each word becomes a v-dimensional vector with exactly one, this one, and the other remaining v minus 1 zeros, right? So one basically denotes the binary position, position of the binary vector, right? So for example, if vocabulary is dog bites man, cat runs fast, so then dog is assigned the positionally we have assigned the index 1, and to all the other indices we have 0 because dog is not present here. Similarly, bites index 1, dog was 0, index 0, bites was index 1, similarly man index 2, and all others are 0. So that's what written here. Critical limitations: dimensionality explosion, vector size proportional to vocabulary size, sparse representation, memory intensive with mostly 0 values, independence assumption, no semantic relationship between words, out of vocabulary problem, requires retraining for new words, storage constraints, impractical for large vocabularies. And the curse of dimensionality: with vocabularies containing 50,000 plus words, one-hot vectors become computationally prohibitive, leading to sparse matrix operations and memory overflow issues. Now we are discussing a bag of words, which is BOW, frequency based representation, right? So in BOW, we represent documents as vectors where each dimension corresponds to a unique word's frequency within the document. This approach treats text as an unordered collection of words, hence the term bag is used. Treating text as unordered collection of words. So each dimension corresponds to a unique word's frequency within the document. For documents, D is equal to D1 till Dn, and vocabulary V is equal to word 1 to word M, WM. Document DI is equal to count WI DI, W1 DI, count W2 DI up till count WM DI. Right. So document 1, let us say, has the cat sat on the mat. This is the string in document 1. Document 2 has the dog chased the cat. So vocabulary is basically all the words. And document 1, we will basically get the frequency of all from document 1. So we have the being used twice. So we add the frequency up as 2. Then cat is seen once in document 1. So 1. Then sat also 1. Then on based on the index as well. And here on is 1. Then mat is being used. So 1. Dog and chase is not used in document 1. So 0 0. And dog chased is being used in document 2, and we are placing it index wise. So you can see we have placed it here, right? And cat is also coming, so cat comes first because we are going according to the indices in this. So as many characters we have here, we will have as many numbers, as many same number of positions here. Advantages of bag of words: fixed length representation, consistent vector dimensionality, semantic document similarity, captures topical relationships, computational efficiency, classification effectiveness. Limitations are order information is lost, no preservation of the word sequence, right? So the order is lost. Then context insensitivity, so same word treated identically regardless of the context. Then common word dominance, so high frequency words may overshadow important terms. Sparsity issues, many zero entries in document vectors. Now TF IDF, going over that. So basically TF stands for term frequency and IDF stands for inverse document frequency. It addresses the bag of words limitations by weighting terms based on their importance within documents and across the entire corpus. So let us break down the formula. Firstly, we have TF, T comma D, where T is the term T and D is the document D. So TF T comma D is basically the number of times term T appears in a document D upon the total terms in document D, right? And IDF T comma D, capital D, is log of total documents in the corpus D upon the documents containing the term T. And TF IDF is basically the multiplication of the two, TF times the IDF. Now, intuitive understanding. So TF IDF increases the weight for terms that are frequently appearing in a specific document, that is, they have high TF, high term frequency of any particular word, terms appearing frequently in a specific document, in one particular document, and terms rarely appearing across the corpus. So in the whole corpus, terms that are rarely occurring in the whole corpus will have high IDF value. So high TF and high IDF, when we multiply, we'll get a high TF IDF rating, or basically a score. So this combination highlights document specific important terms while downplaying common words like the and is, and basically it gives a score. The TF IDF score, the higher the TF IDF score, the more significant the word in terms of the rating. Let us say the corpus is this, right? Now the example. So this is the corpus given to us. This is document 1, this is document 2, this is document 3. For term cat in document 1, we have TF as what? We have basically how many terms? 1, 2, 3, 4, 5, 6. We have total 6 terms, and the term cat is occurring once, right? As you can see, only once. So TF is term frequency in the document. So that is basically number of times the term T appears in the document upon the total terms in the document. So 1 upon this 6. That is the total terms in document D1. So that is 0.167. And IDF is basically log of total documents in the corpus. Total documents in corpus is basically 1, 2, and 3, right? 3 documents in the corpus upon the documents containing the term T. So how many documents contain the term T? That is 1 here, and the cat is also here. So only 2. So log 3 by 2, that is 0.176. So therefore the TF IDF rating would be 0.167 times 0.176. That is this value. Now advantages of TF IDF over the bag of words. So importance rating. So it emphasizes discriminative terms. Common word suppression reduces impact of stop words. Document distinctiveness better captures unique document characteristics. And I'll also share this chat if you want to basically study all these links and all these sources that are given to us. So these go extremely in depth. You can visit these as well. I'll try to cover all these in case you want me to. Just comment down below. So I'll cover all of these topics in depth. Now covering engrams, which is capturing the sequential context. So engrams extends the bag of words by considering sequences of n consecutive words, partially preserving ordered information and local context. Engram types: unigrams we have n is equal to 1. Individual words equivalent to bag of words. Then bigrams n is equal to 2 word sequences. Trigrams n is equal to 3 word sequences, and a higher order engrams increasingly specific context. Example generation sentence. Let us say we have the quick brown fox jumps. Bigrams we create the quick, then quick brown, then brown fox, and then fox jumps. So we are basically maintaining a sliding window. For bigram, the length of the sliding window is 2. So we take 2 per length, right? Let us say we have I comma j here. So I and j would basically move in this format. I moves next, j moves next. Then I moves next, j moves next, right? and it considers two at a time. So that is how bigrams are formed. And trigrams would be in this case with sliding window size of 3. So the quick brown is considered first, the quick brown, then quick brown fox, and then brown fox jumps. Brown fox jumps. So that is trigrams. Now implementation benefits. So context preservation maintains the local word relationships because we are considering windows, or basically sizes of the sentences from which we can easily extract the context of the sentence, right? Now, phrase recognition also captures meaningful word combinations, improved classification, better performance on sentiment analysis and topic classification. Computational challenges, though, we have like exponential growth. Exponential growth, vocabulary size increases dramatically when sparsity amplification, higher order n-grams appear infrequently, memory requirements, storage needs grows exponentially, and overfitting risk, high dimensional sparse representations. Now, talking about vector space models and semantic operations. So, VSM vector space models represent documents and terms as vectors in multidimensional space where geometric relationships reflect semantic similarities. Document term matrix structures looks like something like this: term 1 till term m on the x-axis, and doc 1 till doc n on the y-axis. And this is the matrix that is formed, right? Where Wij represents the weight of term j in document I, typically computed using TF-IDF. Now, cosine similarity and distance metrics. So we have cosine similarity formula: a dot b upon mod of a, sorry, the magnitude of a times magnitude of b. A dot b is basically dot product of vectors a and b, and this magnitude of a is actually Euclidean norm of the magnitude of vector a. Interpretation: if cosine similarity gives us 1, that is identical direction, that means perfect similarity of the words. 0 means orthogonal vectors, no similarity at all. Orthogonal is basically 90 degrees angle between them, right? Cosine is 90, so we have 0 as the answer and no similarity. And 1 is basically same direction, and -1 is basically opposite direction. So they are basically perfect dissimilarity. So for antonyms, we can say good and bad would fall in this category, right? That is -1, opposite direction. Good and a synonym, that is perfect similarity, good, right? Now that is about this. Now let us take a practical example. Let us say document A has these normalized TF-IDF values. Document B has these values. Cosine similarity we calculate for each, right? And we get 0.82, which is high similarity. Now talking about word algebra and semantic operations. So modern word embeddings enable mathematical operations that capture the semantic relationships. Classic examples are king man plus woman is equal to, sorry, king minus man plus woman is actually queen. Gender relationship transfer. All right. So king may say if we remove man and add a woman for the same status, king who's a basically a man as a woman, that would be a queen, right? So status, gender relationship transfer. Then Paris minus France, that is we are removing the country from the capital, plus Italy, which means that is the capital of Rome. So that is why capital city relationships. Walking minus walk plus swim is swimming, right? Grammatical form consistency. So we have vector arithmetic properties, analogy completion, right? And semantic clustering. Similar concepts have nearby vector representations, composition semantics. Combining word vectors approximates phrase meanings. Now talking about word embeddings, then distributed representations. So fundamental paradigm shift. Word embeddings replace sparse, high-dimensional one-hot vectors with dense, low-dimensional representations that capture the semantic relationships. Key advantages over traditional methods: dimensionality reduction. Typical embeddings use 52,000 dimensions versus vocabulary-sized one-hot vectors. Semantic capture. Similar words have similar vector representations. Then transfer learning and computational efficiency. Now, vector space properties. Word embeddings create continuous vector spaces where distance reflects semantic similarity, direction encodes semantic relationships, clusters group semantically related concepts. Training objectives: embeddings optimize for distributional similarity, ensuring words with similar contexts receive similar representations. Now, word to vector architecture and training methods. Generation 1 embeddings. So, word to vector overview. So, word to vector was developed by Microbial and introduced two primary architectures for learning word embeddings: continuous bag of words (CBOW). Skip co-training philosophy was both models, CBOW and skipgram models, learn embeddings by predicting word relationships within local contexts, implementing the distributional hypothesis through neural network training. Now, CBOW is continuous bag of words model, right? So let me show you here architecture and mechanism. So CBOW predicts a target word given its surrounding context words, right? So training process is something like this: context window definition, select the surrounding words within a specific window size. Input aggregation, combine the context word vectors, typically averaging. Prediction, generate probability distribution over vocabulary for target word. Loss minimization, optimize to maximize probability of correct target word. Now, mathematical formulation. Probability of word target given the word context is softmax word target dot average of word context words. So example training instance, sentence given is the quick brown fox jumps over the lazy dog. Context window size is 2. Let us take the training example where context is quick and brown, quick brown, target is fox, right? Now CBOW characteristics, training speed, it is faster than skipgram due to single prediction per context, frequent word performance, better representation for common words, and then it also has syntactic relationships which capture grammatical patterns strongly. And window size impact typically uses smaller context windows, 2 to 5 words. Now we're talking about the skipgram model. So architecture and mechanism, skipgram reverses CBOW's approach by predicting surrounding context words given a single target word. Training process, target word selection, choose center word as input. Context prediction, predict each context word independently. Multiple objectives, generate separate predictions for each context position. Loss aggregation, sum losses across all context predictions. Mathematical formulation, something like this. Objective is equal to summation log of p word context given word target for all context words. Then probability of word context given word target is softmax of word context, sorry, v context times the v target. And you have this example training instance, sentence is the same, context window size is the same, target is fox, context are quick brown fox jumps over, right? So this is quick brown fox jumps over. Generates 4 separate training samples, fox to quick, fox to quick, fox to brown, fox to jumps, and fox to over, right? So basically in this format. Target is given fox, center word we've chosen, fox to quick, fox to brown, fox to jumps, and fox to over, right? 4 separate training samples are there. Now its characteristics, rare word performance, so it's superior handling of infrequent words, semantic relationships, better captures the word meanings and analogies. It can have larger context windows, can effectively use windows of 5 to 20 words, and slower training due to multiple predictions per target. Now architecture comparison, CBOW versus skipgram, decision matrix. So criterion, CBOW and skipgram, we'll be discussing it in a tabular format. Training speed, faster for CBOW because we are only having single prediction. For skipgram, we have multiple predictions, so slower. Frequent words in CBOW give better performance, and skipgram adequate performance. Rare words CBOW's limited effectiveness, but skipgram superior performance. Syntactic relations, strong capture by CBOW. Skipgram a little less than CBOW, so good capture but not strong enough than stronger than CBOW. Then semantic relationships, for CBOW good capture but skipgram has superior capture. Memory requirements, CBOW lower, skipgram higher. Context window size, CBOW smaller, 2 to 5, skipgram larger, 5 to 20. And dataset size, small to medium for CBOW, but skipgram can have large datasets. Now selection guidelines, choose CBOW for fast training, frequent word focus, syntactic tasks, and smaller dataset size. Choose skipgram for rare word handling, semantic similarity, analogy tasks, and larger datasets.